Hello, everyone. Welcome to Ooh, I'm clipping. Welcome to. I'm still clipping. Well, okay. The first lecture, I forgot to turn on the first class. I forgot to turn on the phantom power, and now it seems I have the preamp up too high. Hello, everybody. My name is Scott. University of South Florida. This is calculus. Today we will be talking for section 2. Last lecture was sad. Today we will be talking about the last time we proved the fundamental theorem of calculus. Today we are going to be talking about the two ways to do initial value problems. Yes, this is on the test. The first way, of course, being the way that you were doing it in 4.7. And now we're going to talk about a way to do it that uses the fundamental theorem of calculus part 2. Are there any questions? Chat as usual in Discord. For questions, emote chat on Twitch. You can, do all the little emotes that you want. I need to figure out a way to let other people ask questions on Twitch while having it moderated, but I didn't have time to do that. Maybe that'll be a little summer project. And that's it. Any questions? Nope. Okay. There's emotes, about the last lecture thing. Yeah, it's sad. Okay. So before we begin, let's talk about the quiz. Let's see. Oops, it's giving it away. I wanted to do this. That's still giving it away. Let's see. Ha ha ha. Now it's really giving it away. All right. So how do we feel about this first question, 1 to 5? Stating the fundamental theorem of calculus. We've done it. I told you it would be on every single one of them. The content is still loading on my tablet. There it goes. How do we feel about this one, 1 to 5? All right, so we feel pretty good about stating the fundamental theorem of calculus. As promised, it was on every quiz since test 3 after stating it, because obviously it wasn't on the survey quiz. Maybe next year I'll even put it on the survey quiz, just for kicks and giggles. Okay. Now this second one. This one's a little tricky. You need to break it up. I mean, you don't have to write it explicitly like this. You can leave the thing together. But you do need to you need to break it up so that you get rid of these x squareds. Because what you need are two terms, each one with its own little exponent here. All right. So what I have here is x to the 1/2 over 2 x squared. And I have here x to the 5/3 over x squared. So 1 to 5, how do we feel about the fact that what I need to do is break that up? Okay. Once I've broken it up, I don't know why it keeps going over there. Once I've broken it up, how do I know when I'm going to break it up? Well, I make my little table of integrals. And if I don't see something on my little table of integrals, I start breaking things up. Because that gives me something that's on my table, right? These are power rules, and that I can deal with. And I know that I can break this up on top because it's algebra. Now, this starts getting into how to do integrals. Integrals are more of an art than derivatives are. Derivatives, you're just kind of like, let's go boom, 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 right? There's kind of an algorithmic method of doing derivatives, right? I convert everything into power form, and then I look at it and I go, okay, well, now I use product rule. Oh, the next thing's a quotient. I need the quotient rule. It's a chain. I need the chain rule, right? It's a power. I need the power rule, right? There's all these, it's do this, then do this, then do this. Integrals is a bit of an art, right? You need to break things up. You need more strategies. You have to play with them. But, these are the first ones. And the first thing you want to do, if it's not on your table list of integrals, is break it up. So that's what we did. Now, when I broke this up, I took an antiderivative here, and I did this to here, right? I did -1/2. I need a -2 there. I need a 3/2 because I had a 2 here. Now, let's say I made the little mistake here. I put a negative sign here, right? Because I'm dealing with a negative, so I'm like, oh, I need a negative. Plus C. Well, the point is that if I did that, and I did that on the first time I did it for the last class, so if you want to go back and view the video of me making a mistake and then catching it when I did this, you can. But then what I do is I take my derivative of this thing to catch any little mistake. And I did make a silly mistake the first time I did this because I had a negative here instead of a positive. But then when I took my antiderivative, I noticed I had a negative x where what I needed was a positive x. When I took the derivative of my antiderivative, I noticed that and I was able to fix it. All right, so how do we feel about that, 1 to 5? The whole problem, question 2a. All right. Okay, let's talk about 2b. 2b is genuinely hard. Okay, this one's a hard problem. And there's 2 real methods for getting at this one. Okay, here's 2b. The first is to use FDC1. The first is to shoot for direct substitution and see what you're dealing with. Okay, so the first is not to deal with the integral at all at first. Okay, let's do a little direct substitution and see what happens. Right? Cosine is continuous, and that means that its integral is going to be differentiable, which means it's continuous as well, right? How do we feel about the fact that if this is continuous, the integral of the thing is going to be continuous, the AUC function? So 1 to 5, how do we feel about that? If I have a continuous integrand, if I have a continuous thing in here, I'm going to wind up with this whole function, this AUC function is going to be continuous. I mean, it's differentiable, so it's continuous. All right. So what I'm going to do is I'm just going to do a little direct sub here. I'm going to sub in 0. And I wind up with the cosine of 2t dt from 0 to 0. What is that? I've got no width. Oh, I got no width. What does that mean? That means what I've got is 0, right? I don't care what is in this thing underneath. If I've got no width, I got nothing. How do we feel about that, 1 to 5? If I have no width, if I'm going from 0 to 0, I've gone nowhere. Right? I've got no area. How do we feel about that? Okay, so I've got nothing. Oops, sorry about the bump. Move around a little bit. I'm not facing the camera. I'm kind of facing this way. Okay, so we did this, and we came up with that little bit. So now the bottom here goes to 0. I got 0 over 0. Well, that's a L'Hopital's rule. The derivative of the bottom is very convenient. It's 1. And now what I've got is the derivative with respect to x of the area under the curve there. Well, what's this derivative right here? That derivative's easy. Well, that's by FDC1 That's just the, that's just the area under the curve function. That derivative is the cosine of 2x. And I need my limit here. Well, that's easy. How do we feel about that 1 to 5? I notice that the top is 0 and the bottom is 0, so I do a little L'Hopital's rule. And then I use the fundamental theorem of calculus to tackle this derivative. And because I've got no chain rule here, right? It's just 0 to x. I wind up with cosine of 2x. And that's just, then I directly sub in, because cosine's a nice continuous function, and I wind up with 1. Okay. I don't know what this emote is that I've got in chat. I think it's, boring. So how do we feel about that? The whole kind of combination of steps. All right, that's one way to do it. How else could I get this done? Well, the other way to do it, and that's the easier way to do it. Well, it's not easier. That's the faster way to do it. That's the slick way to do it. It's not so much easier as slicker. Right? You have to recognize this required 2 steps, right? This required understanding that I was looking at no width to apply L'Hopital's rule, and then it required an application of FTC1. So that was slick. Other way to do this type of problem is like this. So I want to figure out what this equals. And what I do is I use FTC2. Well, okay. F of x equals cosine of 2x. Now, this is tricky. How do I deal with the 2? Well, I know that from my little table of integrals, all right, so I do my little table. If I do sine, it's cosine. If I do cosine, I get sine, I get negative sine. And if I do negative cosine, I wind up with a positive sine. So my f is cosine. That means what I'm going to want is a sine. So let's make a guess. Let's do sine of 2x. Now, if I take the derivative of sine of 2x, what do I wind up with? Okay. Well, I end up with cosine of 2x, but then I have a chain. And I wind up with a 2 in the front at the end. So when I take the prime, when I take the antiderivative, I'm going to need to deal with that 2. So I'm going to put a 1/2 in here. And now when I take this, I get 1/2 cosine of 2, and that equals f. How do we feel about that 1 to 5? That is not easy. Okay. Technically, this is called use substitution method for integrals. And I did a very simple one because I wanted to kind of get you kind of prepped up for Calc 2 a little bit. All right. I mean, the better way to do the Calc 1 way to do this is to just do L'Hopital's rule and FTC. Okay. But I kind of, jacked up a little Calc 2 in there. If you do it this way, you need a little bit of Calc 2. That's the first thing that you cover in Calc 2 is the formal way to do that trick, undoing the chain rule. All right, so now I've got FTC2 involved here. I've got my antiderivative here, so I'm going to do 1/2 sine of 2x minus 1/2 sine of 2 times 0. Well, that's just going to be 0. And notice here how I highlighted that. I did that to make sure I was using the right equation. Some people I noticed on some of your quizzes that you keep using f, or after doing all this work, you use the wrong equation. Okay? So one way to stop doing that is to take your test with a highlighter and highlight the g of x that you're actually using. All right. So now what I've got, and this just equals 1/2 sine of 2x. So now what I have is that the limit as x goes to 0 of 0 to x cosine of 2x, I'm sorry, tt dt over x equals the limit as x goes to 0 of sine of 2x over 2x. Now, I could use L'Hopital's rule on this, but come on. 2x over 2x where x goes to 0. And then I just put it that there. Let me get a nice little 1 there. How do we feel about that, 1 to 5? Okay. That one was hard. That one was really hard. Okay. If you have any questions, please type them in. So the way I figured this out, okay, let's do another one. Let's do the one that's on so if you want to solve the one that's on the problem set, okay? What's the one on the problem set? Let's pull that up. The one on the problem set has this. Now, what I'm going to do, when I want to take the antiderivative of this, all right, the 200 just hangs out. Now, I'm going to treat this thing as a block, okay? And I'm just going to say, okay, what if that was the variable? That would be the derivative, antiderivative, right? That would be dealing with the power. And then I have to deal with the fact that there's no 0.5 in front of here. So what I'm going to do is I'm going to put a 2 in front of this. Now what I'm going to do is I'm going to take the derivative, and I'm going to see if I got it. And here, you could actually see it right here. What is the derivative of this bit? That bit's derivative is 1. So I'm okay here. However, here, when I took the derivative of my hypothesis, right? My hypothesis was that the thing was my original g. I said f of x was cosine of 2x. So when I did my original g, my hypothesis was that this was actually sine of 2x. Right? That was the outer. But then I took a derivative of this. We'll call this g bar. That looks like a negative 1. Never mind. So then I took the derivative of this. And what did I get? If I take the derivative of this, I wind up with sine of 2x, right? This is a u. So I wind up with sine of u times du over dx, which equals sine of 2x times 2. And I'm off. Do you see this? When I took the derivative, these two things, I'm sorry, that should be cosine. Right, so when I took the derivative of this, of the outside, I'm off from what my f is. Right, here I've got this 2 that doesn't appear there, but it's a times 2. Well, I know how to deal with times 2. I multiply it by 1/2. Now when I take my derivative, I'm going to wind up with a 1/2 at the bottom, at the front. That's going to cancel that. Oh, that was just sloppy, wasn't it? Yeah. Now when I take my derivative, what happens? I get 1/2 cosine of u times du over dx, which equals 1/2 cosine of 2x times 2. And now I can get rid of the question mark. How do you feel about that 1 to 5? What I'm doing is I'm using the fact that what I'm taking is an antiderivative. So I'm using the fact that I could just take the derivative and see what happens. Okay? Now, formally, what you're going to do the first day of Calc 2 is you're going to do a process called U substitution, which is actually this. It's doing the chain rule in reverse. So that was the idea. The idea was to play with it and see if you could figure it out. All right. Okay, let's go on to this thing. Now, as I said in my announcement, the thing that's tough about these conditions, all but that last one's hard. The thing that's tough about these conditions here is that they're in a weird form. What does this first condition mean? Answer a question. Is the 1/2, so you guys, someone type what that first condition means while I answer this other question in chat. So the question is the 1/2 in g of x related to the f of x? The 1/2 in g of x is related to the u here. That's where that came from. That came from this u. Does that answer your question? Okay. Is someone going to tell me what that first condition means? I'm going to move on to the second one. I want the limit as x goes to positive infinity of f of x equals 0. I'm going to do that right there. And I'm going to draw little asymptote lines right here to make my grader happy. Okay. F is concave up from negative x to from negative 2 to 0. F of 0 equals 0. The area under the curve from negative 3 to 0 is less than 1. Oops, it's got to go all the way to 0. The limit as x goes to negative infinity is 1. F prime of x is greater than 0. Not quite. So I still don't have an answer that... Oh, yes. So someone has given me the answer. Excellent. I'll come to that back in a minute. F prime of x is greater than 0 on negative 1 to 1. Okay, this one means continuous, as was said in chat. Now, what does this one mean? All right, someone tell me what that is in chat. F double prime of x equals 0. That means I've got an inflection point here. And that means that these are going to be concave down. And then I've got this thing. This one's genuinely hard. All right. This says that the derivative at x equals 1. This says f prime of 1 does not exist. That means f has a kink at x equals 1. Because I'm continuous, that means f has to have a kink right there. Okay, this is really two conditions. This is saying that the integral from 1 to 3, f of t dt is greater than 2. And it's saying that for everywhere past it, so this thing right here is saying something very difficult, okay? This statement right here says that I need to accumulate 2 area from 1 to 3, and then I need to never give it up. Okay, so all the conditions, understanding these conditions without this one. Forget the last condition for a moment. How do we feel about all of these other conditions, translating what they mean? 1 to 5. Oh, there it is. Okay. Now let's deal with the last one. Let's deal with these conditions. Let's look at this. This is the hardest portion of the graph, right here around 0. Look at all this stuff that has to be satisfied. Okay? I've got a point. I've got to be increasing. That means I need to go down this way. I got concave up. I've got concave down. This is where all the action is. All right. So let's deal with the places where the action is. All right, what I'm going to do is I'm going to come down here and I'm going to sweep this way a little bit. Right, that will give me negative curvature. That'll give me increasing as I go to the right, which is what I want, and it'll give me concave up. And it will give me negative area, which means it's less than 1. And then what I'm going to do is I'm just going to finish this off because I've got no conditions here, so I can make it do whatever I want. Okay, so how do we feel about that 1 to 5? Meeting all of these conditions right there by sweeping down and then up again, right? I want it to be, it's now positive where I need it to be. I've got concave up, and then I came down here and I hit the derivative. And because I was negative, I'm definitely less than 1. All right, now I'm going to meet this condition. I've got a kink here at 1. I need it to be increasing, and I need it to do something this way. And I notice here that what I need is positiveness, okay? And because what I need over here is positiveness, I'm just going to go up that away. And here I need to stop because I've got a kink. So I'm going to do something concave down so I could satisfy this inflection point condition. And I'm just going to go that away. How do we feel about that, 1 to 5? Just getting a little piece of concave down here so that I satisfy the inflection point. And then I'm going to stop right here because now I'm going to have a kink. Okay. Now, notice I've got nothing here requiring a derivative condition. Okay? There's no other conditions but area conditions right of the curve. I need continuity, but that's the only other condition. Let's go nuts. Right? Let's pull out our old straight edge. The easiest graph in the world to draw is a straight line. Let's pull out our old our student ID here. Let's give it a kink. Let's make it go up. And then it's got to come back down to 0. Yeah, too sharp. Right? I didn't say where it had to go up to. It doesn't need to be smooth because there's no integral conditions. I mean, there's no derivative conditions. Why not? So why not just go nuts here? All right. How do we feel about that? I didn't need anything else. I'll just go up and then come back down. Now, have I acquired the requisite area? So 1 to 5, how do we feel about that? That kind of right side sweep. Now, have I required the requisite area? I need 2 area from here to here. There it is. So I've acquired my 2 area. After, what is that, 3.8? And now I'm not acquiring any negative area. No, I don't need to go up so high. In fact, I could have just gone to here. I didn't even need to do that. I could have gone, right? I could have made this concave up, but stop here at 2 and then just gone straight over. You're right. So my condition that I should have drawn, the question is, but isn't the limit 0 as you must positive? So isn't the limit 0, but you must have positive area underneath. Actually, no, I don't need positive area. I just need non-negative area. That's a good question. I need to acquire non-negative area. Okay, so that's a good point. All right. Well, now let's check. Let's check to make sure our graph meets our conditions. All right, so is this graph continuous? Yes. Is the limit as I approach 0 from the right? Well, it's a straight line, so yes. Am I concave up where I need to be? So from -2 to 2, yep. Is f of 0, 0? That is correct. If I acquired -1 area, I'm sorry, if I acquired less than 1 area from -3 to 0, that was where I wanted, right? -3 to 0. Well, yeah, I've actually acquired negative area. All right. Is my limit correct? Yes. F prime of x is where it needs to be. So from here to here, I'm increasing. Yes. Do I have a kink where I need a kink? Yes. Am I concave up? Yes. I need to be concave up. I'm sorry, do I have an inflection point? Yes. And have I accumulated enough area? Yes. So my graph is done. 1 to 5, how do we feel? And this one's hard. This one is definitely hard. That last condition is. All right. This condition here is just evil. I wouldn't ask that on a test, but that's just fun. These other conditions, though, this is a very good way of testing whether or not you knew these definitions that we asked you to know. So it's a very good way to test whether or not you know continuity. It's a good way to test whether or not you know the prime, those sorts of things. Okay. All right. I went 15 minutes over what I should have done. Okay, well, let's book it. All right, so what we want to talk about is we want to talk about these initial value problems. Okay, so there are a couple ways to do them. Let's do it the first way. The first way is this method that what I do is, let me zoom in. What I do is I take an antiderivative and solve for C. And this is what's done in 4.7. Okay? So what do I do here? Well, I take the integral of f prime, the indefinite integral, and what do I get? Well, let's see, it's x cubed, and then 1/3 that, and then I take the derivative of that, So I wind up with this plus c. I take the derivative just to check. Okay. And then what do? Well, I have a piece of data. So my piece of data is that f of 1 equals 4. And so what I do is I actually plug in for f of 1. Well, now I've just got numbers. So now I've got that 4 equals 1/3. 1 cubed is 1 times 1 times 1, which is 1. I keep forgetting this is a cardioid mic. I need to be more over this way, don't I? It's a good microphone. Thank you. I think the person who recommended it to me is Discreet, but it's a very nice microphone. All right. So are we on board with this? And then I've got this C hanging out. Well, what do I do now? What do I do now, guys? Well, I solve for C. And 4 minus, that's 11 over 3 equals C. So f of x equaled 1/3 x cubed plus 11 over 3. Okay. How do we feel about that 1 to 5? Okay. And that's the way I want to do these on the test. That's the easier way to do it for these, right? In an environment like our classroom, this is the easier way to do it, okay? But in real life, it's not, because in real life, this antiderivative may not be a simple function. Indeed, it may not have a simple function form. It may be something incredibly complicated, okay? There's another way to do these, and that's to use FTC2. Now, recall FTC2 says that g of x minus g of a equals the integral from x from a, sorry, that should be a, from a to x of f of t dt, where g prime of x equals f of x. So I'm going to apply that to this situation. And what I get is the following. I get that the integral from a to x, f of t, so f prime of t dt, because what I have here is f prime. All right, does everyone see that? That what I have here is f prime. So that's really my f. And my g is f. Now, let's look at my data. What piece of data do I have here? The piece of data I have here is f of 1 equals 4. So my a is 1 and my f of a is 4. So now what I have is that the integral from 1 to x f prime of t dt, and I have that, that's x squared, so t squared, equals f of x minus f of 1, which is 4. How do we feel about that 1 to 5? This is just applying FTC2 to this. And as I said before, this is not the most if you're doing this for the test, it's usually faster to do FTC1. But if you're doing these in real life, you're going to want to use this method. Not FTC1. It's generally easier to use the antiderivative method and solve for the C. But in real life, you don't want to do that. So now what I want is I want to find that quantity there. Because what I ultimately want to find is this. So this right here, this quantity from 1 to x is going to be x squared, x cubed over 3 minus 1 cubed over 3, right? Because that's that by FTC2 equals f of x minus 4. That means here, what I wind up with is x cubed over 3 minus 1/3 plus 4. I add 4 to both sides equals f of x. And that gives me that f of x equals x cubed over 3 plus 11 over 12. Oops, sorry, not 11 over 12, 11 over 3. How do we feel about that 1 to 5? Okay, now, why the heck would I do that? Well, does everyone remember those normal distribution things? Where what I wanted to do was find the area under the curve for something? Where what I wanted to do was find something that looked like, let me pull it up. So why would I even bother? Consider a condition like this. Suppose what I want to ask, right? So remember these things here where I would do these things in pre-calc or whatever, where I wanted to know what the population, what percentage of the population was between these two numbers, and that corresponded to an area. That means what I want to do is take the integral of this bit from a to b. How do we feel about that? This idea about these normal distribution problems and these t-distribution problems and all of these things, what I want is an integral from a to b. I want the area under this curve, right? That was the statistics idea. But look at the normal distribution. It sucks. Look at that thing. Raise your hand if you'd like to take an antiderivative of that. Okay. These things are horribly ugly. But I can take an estimate. I can use a Riemann sum. I could do a mid-sum, maybe a little, I could take a left sum, but what I really want is a mid-sum, right? Because what I want to do is numerical. And if you have one of these advanced scientific calculators, right? The scientific calculators. They've got an integral button on them for doing numeric integrals. So if I want a number, okay, if I want a number, that'll give it to me. Which means that if I come back here, suppose this thing is horrible, but I can get an estimate of it. I'm not going to use FTC to do this. I'm going to get an actual number here. And then when I get that number, right, so if what I want to solve for, suppose instead my question was find f of 8 knowing f of 1 equaled 4, right? And I had some awful thing, right? I would have wound up with this equation here. And I know this. And I could estimate this. Does that make sense? I may not even have all of the data I want, but I don't actually care. Okay? Because this thing might be horribly ugly. How do we feel about that, 1 to 5? One to five. How do we feel about this idea that in real life I might have something that looks absolutely ugly, but I could get decent estimates on it? So, not so much on the test, but in real life, this is better. In real life, this is a better way of doing it. Not on the test, but in real life. Okay. Let's do another example here. How much time do I have left? Ooh, I made up some time. Excellent. This is and I just posted an announcement. This is the correct question for this. That exponent should be negative. I had left it positive for some reason. It was correct on the bootleg. It was negative, but it was wrong on the bootleg. So suppose I wanted to produce, right? I've got a firm that wants to estimate the total cost. Now it's got some fixed cost, right? It's got rent. It's got stuff it's got to pay even if it doesn't build anything. And then it's got a marginal cost curve that looks like this. Okay? So what that means is the following. Okay? So what that means, this is what that curve looks like. If we bring up Desmos, we can see the whole curve. Right? And the idea behind this curve is that at the margin, not the total cost, but the marginal cost gets cheaper and cheaper. Once it's cheaper, it's more expensive to produce the first gallon of gasoline. Right? It costs $63 to build the first gallon of gasoline. But the 480th gallon of gasoline costs us $9. Or rocket fuel, not gasoline. And the 880th gallon of gasoline costs us $6.78 to produce. Of course, gasoline is so cheap right now that you go down to, I went down to Wawa the other day and they give me a free tank of gas with any hot dog purchase. Right now, you go to the gas station and you pay for the car wash and they give you the gasoline. So, what do you want? But normally, And the 1,502nd gallon of gasoline, rocket fuel, cost me $5 to produce. So 1 to 5, how do we feel about the fact that as I produce more and more, the marginal cost of producing another unit of gasoline gets cheaper and cheaper? 1 to 5, how do we feel about that? All right. Okay. So now my question is, what does it cost to produce? What's the total cost of producing a gallon of gasoline? Well, the marginal cost, if I plug 1 into this function, right, the marginal costs are going to be 63.246. Okay? How do we feel about that? The fact is that when I take this little number here and I plug it in, I wind up with that as my equation. And then what I do is I take the fixed cost, which was 2,000, and I add it to the marginal cost of producing one, that first unit of gasoline, and I wind up with 2,000 plus 63.246. Well, okay, so my question is, what's the total cost of producing a second gallon of gasoline? Well, the second gallon of gasoline cost me $60, not gasoline, of rocket fuel, cost me $60.30. So I take the total cost of producing a second unit of gasoline is the fixed cost, plus the marginal cost of producing the first unit of gasoline times the gallon, plus the marginal cost of producing the second unit of gasoline times the gallon. So if I wanted to graph that, it would look something like this, right? If I wanted to graph those things, I would say, okay, well, the marginal cost of producing the first gallon is right here. Times the fact that I'm producing 1 gallon. And the marginal cost of producing that second gallon of gasoline, or the cost of producing the second gallon of gasoline, is that rectangle. Right? It's one gallon of gasoline times the marginal cost. So my marginal cost of producing 2 units of gasoline is this rectangle here. I'm sorry, the total cost is producing this is this unit there, plus this unit there, plus the fixed cost. How do we feel about that 1 to 5? Okay, so I'm reading you the question. I'm just kind of using the setup and producing the thing. So my idea is not so much to solve the problem as to talk about the problem. Okay? So my question is, what's the marginal cost of producing the first one? What's the total cost of producing the first one? What's the marginal cost of producing the second one? And then what's the total cost of producing the second one? Well, is there anything special about selling rocket fuel by the gallon? Why not the liter? Why not the half gallon? What if I wanted to sell this by the half gallon? Or produced by the half gallon? What happens if our unit's the half gallon? Okay, well, what's the cost of producing the first half gallon of gasoline? It's M of 0.5 times 1/2. Right? Because marginal cost is in terms of gallons, 1 gallon. So if I'm only making half of a gallon of gasoline, I take the marginal cost of producing a half of gasoline times 1/2 because that's the amount I'm producing. Because note that this is in prices, this is in dollars per gallon. So I'm producing half a gallon of gasoline. Okay, the cost of producing the second half gallon is what? The second half gallon, or else otherwise known as, 2 half gallons or a whole gallon. So the cost of producing the second half gallon of gasoline the cost of producing the third half gallon of gasoline, and the cost of producing the fourth half gallon of gasoline. Okay? So here I have total cost equals the fixed cost plus MC of 1 times 1 plus MC of 2 times 1. Here I have that the total cost of producing 2 gallons of gasoline equaled 2,000 plus MC of 1, plus 1/2 M of 0.5 plus 1/2 M of 1 plus 1/2 of M of 1.5 plus 1/2 of M of 2. What am I doing here? Is there any reason I'm selling by pricing by the half gallon? What happens if I price by the quarter gallon, or the eighth of a gallon, or the 1/100th of a gallon? Is there anything special about that? Of course not. How do we feel about this 1 to 5? That what I wind up doing is a Riemann sum. Now, what is the total cost? What is this fixed cost? That's the total cost. The fixed cost is actually the total cost of producing 0 units. So what I wind up with is that the total cost of Q equals the total cost of producing 0 plus the integral from 0 to Q, the area under the curve from 0 to Q of the marginal thing of x. I have to change my variable, dx. Well, that's just FC2, FDC2. How do we feel about that, 1 to 5? That what I wound up with when I kept iterating this process was the fundamental theorem of calculus part 2. Okay. It's blurry. Ooh. That's no good. How's that? Is that better? Oh, refresh your Twitch. Just hit refresh. That's actually what it is. All right. So, enough with the concept. How do I solve the problem? So, how do I find the total cost of Q? Well, I can do the method of using the I could do the method of using the fact that TC of 0 is the fixed cost equals 2,000 and simply take an antiderivative of the marginal cost. Or I can use the FDC2 method. I'll leave that one to you to do for homework. But let's use the okay. So what have I got? Well, I got total cost of Q minus the total cost of producing 0 equals the integral from 0 to Q of the marginal cost dx. And the marginal cost for 200 times Q plus 9 to the negative 1/5. So oops, this has got to be an X. Okay. How do we feel about that 1 to 5? That's what I want to solve. I want to find that number or that formula. So what I'm going to do is just take an antiderivative here. Okay, again, I'm going to ignore this for the moment. I'm just going to treat this as one big unit. And I'm going to do, this is going to be 200 times 2 times x plus 9 to the 0.5. Yes, and that gives me my checkup. All right, so this is for sum, so I'll call this my G. All right, right, because now when I take the 0.5, that's going to hit that, and I wind up with negative 0.5. All right. So this right here, this means that this bit is going to equal by FTC2 is going to equal this is G. Let's not lose him. So that is going to equal G of Q. Minus G of 0. Okay. There's going to be a 400 there. There's going to be a 400 there. That could come out. Q plus 9 to the 0.5. I can't do anything about you. I'll leave the 400 there. All right, what is the square root of 9? That's 3. And so I wind up with TC of Q equaling 400 times Q plus 9 to the 0.5 minus 400 times 3 plus 2,000. Okay, and that's the solution to the problem. How do we feel about that 1 to 5? I mean, yeah, I should deal with that. Or what is that? 400 times Q plus 9 to the 0.5. Let's do this. This is 1200. That is plus 800. Okay. So that's how I used to do it with FTC2 method. You can also take an antiderivative and solve. And now our class sadly comes to an end. Sad. Okay. So today what we did, I'll bring it back down in just a moment. Today what we did was we talked a lot about initial value problems. We did a few examples. We showed that there were multiple ways to do it. And then we played again. We said why we wanted to do it, because we wanted to estimate things that were ugly. And then we talked about this thing, the dollars per gallon. The rocket fuel problem, and kind of the concept of what I was actually doing was taking a Riemann sum. And I wind up with FTC2 right here. And then I said, okay, well, enough with the concept. How do I solve the problem? And I solved the problem. All right, so a couple things. On Friday, peer leading is optional. I know Laura will be one of the peer leaders. I don't know who the other peer leaders are. I'm not organizing that, but I will pop in and figure out what's going on then. Also, reminder tonight, 7. So Friday's peer leading is optional. You will be going over the test review that is in the that is already online. I have not posted kind of a summary of the thing. I've been busy with Discrete. I will post a summary of all the resources probably this evening or tomorrow morning. Also, I have not posted the bootleg yet. The quiz to take the bootleg proctored. I will do so. Um, what was else of the issues? Oh, and remember that tonight's test review has been moved to 7 because of the test that the Discrete guys are taking at 3:30. You guys have been awesome. I'm so sorry that we ended this way without me being able to see you, without us being able to talk and work some of these problems out together. But, you know, COVID did what COVID did. And I think that, you know, we had a decent online experience as much as it could be. And I'm so, if you think I did a good job, you want to say nice things about me, please go on Rate My Professor and leave me a review. They are, it's actually very important for us when recruiting new students for next semester. So if you think I did a good job, please go on Rate My Professor, leave me a review. My name was Scott. If you think I didn't do a good job, I'm sorry to hear that. Please tell me how I could do better. Please leave me a review on Rate My Professor. My name was Robert Connolly. And I will see you all. Please come by next semester. I love you guys, and I miss you already. Please come by next semester with this whole COVID thing. Come by my office, say hi. Hopefully by then I will pass my other qualifying exam for my PhD as well. So I'll be happy to see you either way. And it'll be, you know, so please come by. Don't be a stranger. Any questions? Other questions? Okay. I don't know what's going on for the summer. I know I'm not teaching formally. At least they've told me that they found enough people. But I will probably be doing something on Twitch because I want to do more videos like this. Because I think I'm going to flip the pre-calc class and maybe the calc class next semester. So if you miss me, I may be around on Twitch. And anyway, have good luck on your exams, and remember the reviews. And I will talk to you all later. And I have office hours now. Bye-bye.